Andrew Tech Videos presents Study of Electrical Power Factor, COS.
Power factor. The basics. Question 1. What is power factor? Question 2. What causes low power factor? Question 3. Why should I improve my power factor? Question 4. How do I improve my power factor? Question number 1. What is power factor? Power factor of an AC electrical power system is defined as the ratio of the real power flowing to the load to the apparent power in the circuit. Power factor equals kW/kVA. To understand power factor, we'll first start with the definition of some basic terms. Active power in kW, reactive power in kVA, apparent power in kVA. Active power in kW. Active power is working power, also called actual power or active power or real power. It is the power that actually powers the equipment and performs useful work. Real power formulas. P equals VI, in DC circuits. P equals VI cos theta, in single-phase AC circuits. P equals square root of 3V allele cos theta or, in three-phase AC circuits. P equals 3V phase I phase cos theta. P equals square root of, S, Q, or. P equals square root of VA-VR, or. Real or true power equals square root of, apparent power, reactive power, or. kW equals square root of, kVA-kVR, apparent power in kVA. It is the vectorial summation of kVAR and kW. Apparent power formulas. S equals VI. Apparent power equals square root of, true power plus reactive power. kVA equals square root of kW plus kVAR. Also note that resistor absorbs the real power and dissipates in the form of heat and light. Inductor absorbs the reactive power and dissipates in the form of magnetic field. Capacitor absorbs the reactive power and dissipates in the form of electric core. Electrostatic field, power factor analogy. Power factor PF is the ratio of working power to apparent power. Power factor equals kW, kVA. Power factor analogy 1. Looking at our beer mug or Lay's packet analogy above, power factor would be the ratio of beer, kW, to beer plus foam, kVA. Power factor equals kW plus kVAR. Equals beer/beer plus foam. Thus, for a given kVA, the more foam you have, the higher the percentage of kVAR, the lower your ratio of kW, beer, to kVA, beer plus foam. Thus, the lower your power factor. The less foam you have, the lower the percentage of kVAR, the higher your ratio of kW, beer, to kVA, beer plus foam. In fact, as your foam, or kVAR, approaches zero, your power factor approaches. Our beer mug analogy is a bit simplistic. In reality, when we calculate kVA, we must determine the vectorial summation of kVAR and kW. Therefore, we must go one step further and look at the angle between these vectors. Power factor analogy 2. Let's look at another analogy. Mac here is dragging a heavy load. Mac's working power, or actual power, in the forward direction, where he most wants his load to travel, is kW. Unfortunately, Mac can't drag his load on a perfect horizontal. He would get a tremendous backache, so his shoulder height adds a little reactive power, or kVAR. The apparent power Mac is dragging, kVA, is this vectorial summation of kVAR and kW, power triangle. The power triangle illustrates this relationship between kW, kVA, kVAR. Question number 1. What causes low power factor? Since power factor is defined as the ratio of kW to kVA, we see that low power factor results when kW is small in relation to kVA. Remembering our beer mug analogy, this would occur when kVAR, foam, or mass shoulder height, is large. What causes a large kVAR in a system? The answer is inductive loads. Inductive loads. Inductive loads, which are sources of reactive power, include transformers, induction motors, induction generators, windmill generators, high-intensity discharge, HID, lighting. What causes low power factor? These inductive loads constitute a major portion of the power consumed in industrial complexes. Reactive power, kVAR, required by inductive loads increases the amount of apparent power, kVA, in your distribution system. This increase in reactive and apparent power results in a larger angle, measured between kW and kVA. Recall that, as increases, cosine, or power factor, decreases. So, inductive loads, with large kVAR, result in low power factor. What causes low power factor? So, inductive loads, with large kVAR, result in low power factor. Question number 3. Why should I improve my power factor? You want to improve your power factor for several different reasons. 1. Lower utility fees by a. Reducing peak kW billing demand. Recall that inductive loads, which require reactive power, caused your low power factor. This increase in required reactive power, kVAR, causes an increase in required apparent power, kVA, which is what the utility is supplying. So, a facility's low power factor causes the utility to have to increase its generation and transmission capacity in order to handle this extra demand. By raising your power factor, you use less kVAR. This results in less kW, which equates to $1 savings from the utility. B. Eliminating the power factor penalty. Utilities usually charge customers an additional fee when their power factor is less than 0.95. In fact, some utilities are not obligated to deliver electricity to their customer at any time the customer's power factor falls below 0.85. Thus, you can avoid this additional fee by increasing your power factor. 2. Increased system capacity and reduced system losses in your electrical system. By adding capacitors, kVAR generators, to the system, the power factor is improved and the kW capacity of the system is increased. 2. Increased system capacity and reduced system losses in your electrical system. Example. For example, a 1000 kVA transformer with an 80% power factor provides 800 kW, 600 kVAR, of power to the main bus. 1000 kVA equals square root of 800 kW, plus, calculating kVAR. Hence kVAR equals 600. By increasing the power factor to 90%, more kW can be supplied for the same amount of kVA. 1000 kVA equals square root of 900 kW, plus, calculating kVAR. Hence kVAR equals 436. The kW capacity of the system increases to 900 kW and the utility supplies only 436 kVAR. The kW capacity of the system increases to 900 kW and the utility supplies only 436 kVAR. Uncorrected power factor causes power system losses in your distribution system. By improving your power factor, these losses can be reduced. With the current rise in the cost of energy, Increased facility efficiency is very desirable. And with lower system losses, you are also able to add additional load to your system. 3. Increased voltage level in your electrical system and cooler, more efficient motors. As mentioned above, uncorrected power factor causes power system losses in your distribution system. As power losses increase, you may experience voltage drops. Excessive voltage drops can cause overheating and premature failure of motors and other inductive equipment. So, by raising your power factor, you will minimize these voltage drops along feeder cables and avoid related problems. Your motors will run cooler and be more efficient, with a slight increase in capacity and starting torque. Question number 4. How do I improve my power factor? Decrease power factor. Reactive power, inductive loads, are decreased power factor. 1. Transformers. 2. Induction motors. 3. Induction generators, windmill generators. 4. High-intensity discharge, HID, lighting, increase power factor. Reactive power, capacitive loads, are increase power factor. Capacitors, synchronous generators, utility and emergency, synchronous motors, increasing power factor. 1. Installing capacitors, kVAR generators. 2. Minimizing operation of idling or lightly loaded motors. 3. Avoiding operation of equipment above its rated voltage. 4. Replacing standard motors as they burn out with energy-efficient motors. 1. Installing capacitors, kVAR generators. Installing capacitors decreases the magnitude of reactive power, kVAR or foam, thus increasing your power factor. Reactive power, kVARs, caused by inductive loads, always acts at a 90-degree angle to working power, kW. Inductance and capacitance react 180 degrees to each other. Capacitors store kVARs and release energy opposing the reactive energy caused by the inductor. The presence of both a capacitor and inductor in the same circuit results in the continuous alternating transfer of energy between the two. Thus, when the circuit is balanced, all the energy released by the inductor is absorbed by the capacitor. Following is an example of how a capacitor cancels out the effect of an inductive load.
Thank you for watching. Please subscribe Andrew Tech.